Hi, this video segment is going to be on matter and formulas and a little bit about chemical reactions. So I'll go ahead and get started. Again, these are the notes that you'd find if you went onto Moodle and downloaded these guys. And it's my lecture notes for a portion of chapter number 1. So everything around us is matter. There are very few things that aren't matter. Matter is anything that has mass and occupies space. So occupying space is the equivalent of volume. So a baseball has a smaller volume than a softball. And so the amount of space that those takes up is different. And so if I'm mass, I do take up space. Even if I'm something like air, I take up space. And we know this because we can take that mass and put it into a balloon and have that balloon get bigger. So that air is taking up space. The mass part, I want to make sure that we get this. This is just a measure of the amount of matter that's there. And so in this case, we're talking about stuff, and then stuff in this context is atoms. And I want to make sure that we know that mass and weight are not the same thing. Weight is gravity acting on mass, and mass is the amount of stuff. So if I take an object like a baseball and I take it to the ocean, it's going to have a certain weight, but it's going to have the same amount of mass. If I take it to Denver, it's going to have the same amount of mass, but it's going to have less weight. It's further from the center of the closest gravitational body, Earth. And so then the amount of gravity acting on that baseball is less. So it will have a smaller weight, which is why if you're in Coors Field, you're more likely to see a home run hit than if you're in, say, Houston, Texas, because it's basically sea level in Houston, and you're at 10,000 feet. And in Denver, is it 10,000? I know it's at least a mile. So that's 5,000 feet. Maybe it's not 10,000, but it's up there. If I take an object like a Frisbee to the moon, it's going to have a mass of 175 grams, just like it does here on Earth. But on the moon, the Frisbee has a weight of 1 ounce, and here it has a weight of 6 ounces. So there's 6 times more gravity. And you can imagine that that was kind of a conundrum for astronauts when they went up there, because the rockets that they left Earth with were huge. And the rockets that they had ready to go to leave the moon were not huge. And so they needed to make sure that that calculation was correct. So even though those rockets were much smaller, they were powerful enough to get them to leave the moon. And obviously they were, because Neil and Buzz came home. Okay, so I need to take that definition of what a matter is. I need to break it up into basically 4 components. We're going to divide it in half and then divide those halves into quarters. So we're going to have pure substances and mixtures. The pure substances have fixed properties, meaning if I've got a sample of a pure substance, all the way through that substance is the same thing. Top, bottom, middle of the container, everything's exactly the same. The composition is the same. Fixed properties. And the other part of it is I can't physically break this molecule or this atom into smaller objects. So if I'm talking about gold, I can't take a gold atom and hit it with a hammer or whatever else, burn it, can't do anything to it to actually cause it to change chemically. I could put them in an atom smasher, but that's not the same thing. That's not really chemistry. The mixtures, on the other hand, the composition is different all the way through. An easy example of mixture is pizza. Sometimes I take a bite of pizza and there's like very little sauce or no sauce. And sometimes there's no cheese on that spot or there's no pepperoni on that spot. So the proportions are different all the way through. And if I don't like something that's on the pizza, like pineapple, I can pluck that off. So I can physically separate the mixtures into their individual components. And that's not something you can do with a pure substance. So now I'm going to take the pure substances and divide those into 2 more categories. Categories are elements and compounds. The elements are all the atoms off the periodic table, so all 118 of them. If I've got a sample of an element, it's just that one atom type. There isn't anything else with it. And I can't, again, break that thing apart chemically because it's as busted down as it can possibly be. So I like to think about elements like Legos. So a single Lego would be like an element. I'm not going to cut the Lego with like a hacksaw. It's as broken down as it possibly can. But then if I want to make something with the Legos, that would be like the compound. So I can take the Legos and put them together and make something. I can take atoms and put them together and make a molecule. That molecule cannot be physically broken apart. Again, I can't use a hammer or a saw or whatever to bust it apart, but I can use chemistry to break it apart. So what I mean by using chemistry to break it apart is I could use electricity, I could use another chemical reaction, I could use something that's, if my element is gold, I can make a molecule of gold that's got 3 fluorine molecules on it. So this can't be broken down, period, at all, using any kind of chemistry. This, on the other hand, I could potentially break down into gold and 3 different fluorine atoms. That is definitely possible using some chemistry. Something more likely that would happen is I could get my gold back. I could take this molecule here and I could throw in, I don't know, some copper, and then I could get my gold, my pure gold back, and now I've got a molecule that's got copper. It's probably going to be something like that. And we're worried about why a fluorine atom disappeared here, but we'll talk about that later. The gold has now been separated out. So I did separate gold from the fluorine, but I did that using chemistry. So there's a chemical reaction that occurs where in this case, the copper is giving the gold some electrons, and then we get regular gold back instead of this gold 3 fluoride molecule. Okay, so those are the elements and compounds. And if I want to bust apart if I want to move on to mixtures, which is the other half of this, I have 2 types. I've got heterogeneous, which means different, and I've got homogeneous, which means the same. So sometimes a mixture looks the same, and sometimes a mixture looks different. You can obviously see that that's a mixture. So tapioca pudding is a good example of heterogeneous. You can see the pudding, and you can see the balls of tapioca protein in there. If you don't like them, you can pull them out. Bad milk is not homogeneous. You see that word on the side of a milk container, and you're expecting that when you drink the milk, the first taste you have of the milk and the last taste you have of the milk are exactly the same. And so that would be homogeneous. If it went bad, that would be not homogeneous. Water with sand in it is also an example of non-homogeneous. I could separate those things out. So with the sandy water, I could just run the water with the sand in it through a filter, and then now I've got water and I've got sand. So they're separated from each other. Homogeneous, butterscotch pudding. It looks the same. The top, the bottom, and the middle, it's all the same. So maybe it could be of a pure substance, but it's not, because if I left the lid off the butterscotch pudding, it would evaporate off water molecules, and evaporation is not a chemical process, it's a physical process. Milk, when it comes out of the cow, is homogeneous, but then when you let it cool and settle, it actually disassembles itself. You can buy non-homogeneous milk at, say, a grocery store. I wouldn't advise it. It's like cheese on the top and white water on the bottom. Not pleasant. You have to shake the heck out of it to get it to turn back into homogeneous milk. And then salt water, you just take 2 glasses of water and you sprinkle some salt into one of them. You can't tell the difference between them unless you taste them, or unless you just wait and allow one of them to evaporate off, and then you'll see where the salt is. So we can separate these mixtures by physical means, which we can't do with the elements or the compounds. Okay, so here are my elements. My elements are these 118 things, and they start off with hydrogen and they end in organium, which is a man-made molecule, man-made atom that has no real use. I doubt somebody's going to find a use for it in the future, but we made it, so yay. Most of the time it's 2 symbols for the element, but sometimes it's just a single. And almost always the symbols correlate back to the atom. So like C is carbon and N is nitrogen and O is oxygen, but that's not always the case. We've got 11 of them basically have their symbols rooted in some either history or political issue. So for these guys here, we have known about these elements for a long time. We named them a long time ago, and so we've kept the symbols that are associated with the name. So the old name for gold was Orium. So in a breath of nostalgia, we decided to keep AU for the symbol for gold, even though obviously there's no A or U in the word gold. And so we've got that for 8 of these. And then the last 3, this was about different organizations discovering those elements, and as a compromise, they would allow one of the organizations to name it, and then the other organization got to pick the symbol for it. So easy example, tungsten was discovered by two different groups, and the German group wanted to call it wolfram, and I can't remember who maybe I think it was possibly Swedish, Scandinavian in some way, maybe Nordic. Anyway, they decided to call it tungsten, and Germany wanted to call it wolfram. So what they decided to do is use the W from wolfram for the symbol, and then the name tungsten is what we use. Something that is kind of nice, if you're watching this video, you're probably a English speaker, and chemistry's language is English, just straight up English. You can talk chemistry with somebody from any country if they've learned chemistry. It's the official language. So in grad school, there were a dozen people in my grad school class from Thailand. We couldn't talk about ordering lunch, but we could talk about chemistry all day because the words are the same. So if you're an English speaker, you got that going for you. You don't have to learn a new language. Okay, so molecular formula. So this, we talked about the elements, and so you can get those by just looking on the table. If I want to take and create a compound, I'm going to take more than one element and put it together and make something. So I've got a water molecule. Great. So water molecule is an H and an H and an O. And if I put those things together, I get a water molecule. If I put them together any other way, it's not a water molecule. So I need two H's and one O, and that's my water molecule. I know there's no one written down here next to the oxygen symbol, but we're not going to write a 1 there. We're just going to assume that if nothing's written, there's going to be a 1 there. In the same way that this is sulfuric acid. So this is showing that there's 2 hydrogens and 4 oxygens. And since there's nothing written for the S, there's 1 sulfur there. And that's it. All this is telling you is which atoms and how many of those atoms. It is not telling you how they get connected up to each other. So it's a limited, but still helpful way to talk about what the atoms are. If I'm using the Lego analogy, it would be like somebody saying there's 2 blue Legos and 1 white Lego and 4 black Legos connected up, but not telling you how they're connected up to each other. All right, and then the last thing we're going to talk about for this little video is a difference between a chemical change and a physical change. In a physical change, the formula or the molecule or the atom, everything about it stays the same. It just changes form. And the easiest way to talk about that would be a water molecule that is a liquid. So that's a lowercase cursive L in parentheses as a subscript, and that's how we describe something as a liquid. And I can turn this into a solid, a lowercase s that's subscripted. So I take this liquid water and I put it in the freezer and I get solid water. It's still H2O regardless. They are definitely not the same thing. You're not going to dive off of a diving board into solid water, but it's still water. So that's a physical change. A chemical change, on the other hand, we would be doing something like a water molecule being exposed to electricity, some kind of voltage, producing hydrogen gas and oxygen gas. You can absolutely see this yourself if you take a 9-volt battery, and the 9-volt batteries are the blocky looking ones with a little electrodes on top. Sometimes they're in smoke detectors. If you were to take this and put it into a glass and put water in the glass and then put a tiny bit of salt in there, you would see a bubble here. And then you would see another bubble here. And one of them will be twice as big as the other. The one that's twice as big is hydrogen, and the smaller one is oxygen. Because to make this formula work, I'd need to have 2 water molecules making 2 hydrogen molecules and 1 oxygen molecule. And we'll talk about the 2s that are here and why the hydrogens and the oxygens are paired up a little bit later, but that's the situation. So this H2O is different than H2 and O2. So this is a chemical reaction. A chemical change has occurred. I have another example about isopropyl alcohol, rubbing alcohol. If you take rubbing alcohol and you put a drop of it on your skin, say you're disinfecting a wound, it'll evaporate away, but it's still isopropyl alcohol. It's that smell that you recognize when you walk into a hospital because everything is, hand sanitized. They use ethanol and isopropyl alcohol a lot, and your nose smells that alcohol. But if I take that isopropyl alcohol, I can burn it, and you can like spray it on a fire and then put a match to it and it burns. And when it burns, the isopropyl alcohol, which this is its formula here, C3H8O, if you burn it with oxygen, you end up making H2O and CO2. So these two things are definitely different than those two things. So that is a chemical reaction that has occurred. How do you know a chemical reaction has occurred? There's three easy indicators. Something changed colors. So an easy example of that is a marshmallow that you put into the campfire goes from white to black, or preferably from white to light brown. You have performed a chemical reaction. That marshmallow tastes different when it's lightly browned. It's called the Maillard reaction, and you have caramelized that sugar. It is turned into something different, and that's why its color changed. Another example would be presence of a gas. If you take some baking soda in your kitchen and you dribble in some vinegar, you will get a gas. You didn't heat anything. All of a sudden, there are bubbles where there weren't bubbles before. So what that means is you created a substance that is a gas at this temperature and pressure, and that substance in this case would be carbon dioxide. And the last one is the formation of a precipitate. This one isn't super common to most people, but let me pull up a picture. So go to pictures, go in, scroll down to precipitates. Precipitates. There we go. Here's probably the best one. So if we zoom in on this, you can see that this looks like water. It's clear and colorless. And what's coming out of this little pipette is clear and colorless. But when they come in contact with each other, I get this yellow solid, yellow solid, yellow solid, yellow solid. So those yellow solids, that's a chemical reaction that has occurred. This is lead to chloride, meaning in this up here, there was either a lead ion or chloride ions, and down here, there was either the opposite, the chloride or the lead ion down here. And so when they came together, lead and chloride in a liquid solution form a solid. And so this will literally settle on the bottom, and then you'll have this solid powder on the bottom, and then you'll have this liquid up top. You could use filter paper to separate them out, and I just saw a chemical reaction occur. When I was in the Navy on watch, depending on which watch I was at, if I was in the engine room, looking after the generators, I had to do this reaction every 15 minutes. And so what I did is I took we actually had test tubes down there in the engine room, and I would dribble out a little bit of water off of a steam trap, and I would put it in there. And so this would be water from the piping that we used to run the generator. So a generator, at least on an aircraft carrier, is a giant axle. On one end, there's a whole bunch of wires with magnets, and on the other end, there's a turbine. And the turbine is just the thing that gets pushed. So in this case, we use steam to push the turbine blades, and the turbine blades spin, and then you end up getting the generator side to spin. And so what I do not, under any circumstance, want is salt in that water. If there's salt in that water, I can get these pipes, these steam pipes, to leak. And if they do, I'd be dead in about 15 seconds. That's about how long I'd last. Steam coming out of those pipes would cauterize the air sacs in my lungs, and then I'd die immediately. So I want to make sure that doesn't happen. It takes about a half an hour for salty water in the steam system at 700 degrees to eat its way through a metal pipe. So what we do is we take this sample of steam that's been turned into water, liquid, and to it I add something called silver nitrate. And it's dissolved silver nitrate, and dissolved, the word for dissolved is aqueous in chemistry. I put that in here, and if there is a white precipitate, DPT is the abbreviation for precipitate, nobody gets to shower for a week. While I was on the ship, that happened 3 different times. Imagine what an aircraft carrier, which I know it's on the ocean and it's got a deck. For the most part, we're required to stay inside, because when we're flying planes, you can't be outside. And we fly planes a lot. You'd imagine what 6,600 guys, because at that time there were no women on the aircraft carrier, smelt like after a week of nobody showering. It's not a pretty, it's not a good smell, especially in like the cafeteria, the galley where everybody would be. So if there's no white precipitate that forms, then I know that there is no, the white precipitate that forms is AgCl, which is a solid. And so if there's any NaCl, aqueous, so dissolved salt that's inside my steam sample, then if I added the silver nitrate to it, I'd end up with this white precipitate and I'd have this silver chloride stuff. But that never happened to me. I wasn't on watch when that actually happened. But it happened to 3 different people while I was on the aircraft carrier, and hence the no showering for a week. It was at least a week. Okay, that's all I got for this video. Thanks for watching.